Hello, my name is Kenneth Wagner. I'm an electrical and computer engineering student from Rowan University, and today I'm presenting my research on the development of a wireless bus CubeSAT interface. So first, I would like to talk about a little bit about what is CubeSAT. So CubeSats are basically small modular satellite platforms that are capable of carrying scientific payloads. You can see an example of a 2-unit CubeSat here. So the 1 unit would just be one of these cubes, and then 2 unit would be these cubes. And you can see the payloads in there, along with all the other subsystems responsible for power and communication with ground and orienting the satellite. So in the past decade, we've seen an exponential growth for CubeSat platforms. We've seen about 1,500 launches in the past 10 years, and we believe this is due to the lower development time and launch costs compared to traditional satellite launches, and thus we're able to enable more access to the low Earth orbit environment for scientific payloads and research. So with this popularity, however, we've noticed some issues with the current wired interconnect that CubeSat launches use. So they currently use a wired interconnect to facilitate communication and power delivery between subsystems in the form of the PC104 header. So some potential problems with this is it takes extensive pre-planning and assembly, since you need to run all these wires manually. There's potential failure points when you're constantly plugging and unplugging these connections when you're testing and making sure things are working. You're limited in your post-launch reconfiguration, since these connections cannot be changed once you're in orbit. And the header takes up a relatively large volume requirement compared to the total CubeSat volume. So our proposed solution for this was a Bluetooth-based wireless CubeSat interface that would replace the wired communication. We'd be able to save on board space, since you don't need the whole header. You'd be able to reduce the pre-launch assembly time, since there's not nearly as many wires being run, since you're going to be worrying about power delivery. We'd be able to reduce the risk of data loss from mechanical failure, since you're not constantly unplugging and plugging in pins during assembly. And you're able to enable post-launch reconfigurability, since you're able to dynamically change which subsystems are connected to which. And we chose BLE as the solution for this due to its superior performance compared to other protocols such as Zigbee and LoRa. So this is the operational setup that you would use. So in terms of command and data flow, we'd have our CNDH, which is our command and data handling module. And this is kind of the brains of the CubeSat environment, acting as the BLE client role. And then all other subsystems would act in the BLE server role, and then they would communicate via BLE write commands and BLE notifications, which you can see in this picture here. And to realize this into an actual design, we utilize the Nordic NRF52833 system on a chip, which we were able to use to create a custom BLE prototype PCB to simulate the typical CubeSat data transmissions that would take place in a setup such as this. You can see them on the breadboard there, and these are the dev kits that we use to program them. So in terms of performance constraints, we constrained ourselves to power consumption, latency, packet error rate, and throughput. So in terms of power consumption, ideally we'd be within 5% of our total power budget, which is around 70 milliamp hours for all subsystems. In terms of latency, we want this to be as low as possible and comparable to a wired interconnect. In terms of packet error rate, this is basically the amount of packets failed versus the total packets received, and we would want this to be within 2% for all scenarios. And then for throughput, we have a 90-minute orbit, and in that 90-minute orbit, we need to send about 100 megabytes of data to the ground station in that orbit, so we need to make sure that our throughput is high enough to accommodate that. So in terms of experimental results, each test was measured using a 100 megabyte test file at -4 dBm transmit power and 10 centimeters between each subsystem. So in terms of power consumption, we had an average of about 14.61 milliamps while actively transmitting and 0.86 when idle. In terms of latency, we had an average latency of 3.2 milliseconds, and in terms of packet error rate, we had a packet error rate of 0.45%, and in terms of throughput, we found an average throughput of about 1,230 kilobits per second, which took about 11 minutes to send. So in conclusion, this throughput demonstrates that we're able to handle the 100 megabyte data requirements on each orbit. The power consumption of 1.3% was far below the 5% expected. The latency of 3.2 milliseconds was much lower than the previous research that was conducted of 7.1 milliseconds, and our packet error rate was well within our 2% constraint. So in the future, we'd like to perform thermal vacuum testing to measure the performance in an environment that's closer to low Earth orbit. And we'd like to perform interference testing to identify the strength of internal reflections and near-field effects. So I'd like to thank Rowan University for giving me the tools to perform this research, and I'd like to thank NJSGC for funding my research. Thank you.